Well, good afternoon. I'm John Sangenberger, and I am Executive Director of Alumni Relations here at the Tepper School. It's been my honor since 2001 to lead our Alumni Relations team, and we're so glad to welcome all of you back into the virtual classroom today for our webinar on the principles, potential, and pitfalls of generative AI. It's our third in a new series sponsored by the Tepper School's Center for Intelligent Business on the impact of generative AI or Gen AI on business and society. Before we begin our presentation, let me give us a few announcements here. Our next webinar will come up next month on Monday, November 13th. We'll be talking about Gen AI for workplace communications with one of our professors, Emily Desjeux. So I think you'll be really impressed by that and have some practical applications in your communication at the office and in your life. We also want to tell you about our upcoming MBA alumni reunion and save the date for April 19th and 20th, 2024. It's going to be for the classes of 4 and 9 with a one-year reunion for the class of 2023. But it's also a very special year with our 75th anniversary beginning of the GSIA back in 1949. Also the 20th anniversary of the naming of the Tepper School in 2004. In addition to our MBA reunion, the weekend before, we have Spring Carnival and Reunion Weekend for our undergraduate alumni, same for classes of 4s and 9s, and the one-year reunion for our undergrads in 2023. So mark your calendars for that if you're one of our undergrad alumni. We are also accepting Alumni Award nominations now for the 2024 Tepper School Alumni Awards. You can click on the screen here or go to our website. We'd love to have your nominations in so that we can, again, select some outstanding alumni to represent our alumni community. If you haven't made your annual contribution to the Tepper School to help support our academic mission of the school and our outreach to alumni like today's webinar, we encourage you to do that. Giving CMU Day is coming up on November 28th, but you can start to make your contributions now if you haven't done it yet. Well, I think we're ready to begin, and I'm really honored to be able to introduce one of our new professors here at the Tepper School, Professor Karan Singh. He is Assistant Professor of Operations Research here. He joined us last year in 2022. He received his undergraduate degree in computer science from IIT in Kanpur, India, and then came to the US to earn his master's degree and PhD in computer science from Princeton University. There he was awarded the Porter Ogden Jacobs Fellowship, their highest honor for a graduate student. So we're really honored to have him here. He spent a year in postdoctoral research at Microsoft Research in Redmond and brings to us a real passion for theory and algorithms for machine learning and optimization and Gen AI, all the things we're going to talk about today. So we're really glad to have him. He comes to us and joins our faculty, as we always do, bringing in the top faculty from around the world to come and teach at this incredible university. So I'm happy to hand it over to Professor Karan and let you go ahead and lead us.
Thanks, John. Great. So thanks for joining me on this seminar on principles of generative AI. And although the officially advertised title of this talk is Principles, Potential, and Pitfalls, I'll mostly focus on the principles part of generative AI. And I'll say why that's the case. Why am I specifically focusing on the principles of generative AI? And my name is Karan. And maybe what I'll do is I'll start with the introduction of who I am, what's my background, and then I'll tell you why specifically am I giving this talk, what's my interest in generative AI. Okay, so just a moment. Okay, great. So I am an assistant professor of operations research at the Tepper School. And my journey towards machine learning and AI has been a circuitous one. So I started as a graduate student at Princeton. And then while I was a graduate student at Princeton, I was a very early member of this very small startup on AI and machine learning called Innate, which was then acquired by Google Brain. And then I spent a part of my PhD as a part-time researcher at Google Brain before it was Google DeepMind. And after that, I spent an year at Microsoft Research. And now, finally, I'm at Tepper. I joined Tepper maybe last year, sometime in 2022. And throughout all of my research and professional journey, my focus has been on machine learning and optimization. And the interesting part about being in this machine learning and optimization space is that all of the new developments in machine learning, all of this stuff that makes people excited, started happening around the time when I started my undergrad. So in 2012, there was a major breakthrough in machine learning that brought the spotlight onto deep learning, which is a sort of one specific way of doing machine learning. And that has created shockwaves in other parts of machine learning. And we'll see what those shockwaves are. So I'll take, because of my own journey, a somewhat historical take on generative AI. We'll get to see how generative AI came about, what are the basic pieces of technology that make generative AI possible. Okay, and this is about me, but I would like to maybe give a slightly broader introduction to an introduction about us. So the way I'll introduce us, meaning me and my colleagues who are interested in generative AI at the Tepper School, is I'll ask you a very simple question. Fine, and this question, it's supposed to be something just to get you started, but it's not related to generative AI, not at least in a direct way. Okay, so the question is this. You have to tell me what piece of technology am I talking about? And I'll give you some brief history of what this technology is. So it was a piece of tech that was maybe invented or at least put into first use in the military. So it was actually maybe invented by the Department of Defense in something like 1970s, early 1970s. It wasn't broadly used before at least the 2000s. And even before 2000s and since 2000s, it has seen widespread consumer and business adoption. And it's so widespread now that I think we take it for granted. And in fact, it has made its way into gaming and a lot of other things that we think about as pleasure rather than business. Okay, so this is a very generic sort of introduction to what this technology is. So a lot of answers might fit this way of describing the cycle of technology adoption. So here specifically, and again, multiple answers could be correct. One answer that fits this paradigm is Global Positioning System, or GPS. So GPS was indeed invented by the US Department of Defense somewhere around 1970s. And it was early on used in commercial navigation, for example, on boats and ships, which used to take long hauls. And since 2000s, especially since release of iPhones and consumer-grade GPS systems, we see them in commonplace pieces of technology, like mobile phones. And indeed, there are mobile phone games that actively make use of GPS to shape the customer experience, right? So here is a very popular game. It's called Pokemon Go. And the point I want to make with this example is that it's not very easy to see how a given piece of technology is going to affect society. What are it's going to be its potential use cases? And if you think this is still reasonable, that tech that's originally developed for defense gets used by public, becomes a tool for enjoyment, then maybe you would agree that at least the next news article that I'm about to show you, maybe is not that easy to predict, that people, and specifically criminals and robbers, could use something like Pokemon Go to get people to certain isolated locations, and then, yeah, they would commit crimes, they would rob these people. So it's starting from something like in 1970s, there must have been scientists who saw the value of GPS, but even they would have had a hard time predicting that at some point, this will become such a popular tool that at some point, yeah, like there'll be games around it, and people will actively make use of the fact that people play these games to rob people. I think that's a really far stretch in imagination. So in some sense, the sort of layering that we have of reality it's multi-level steep, and it's very hard to make predictions about new pieces of technology. And that's why at the Center for Intelligent Business at the Tepper School, which is a multidisciplinary center, what we have done, and specifically this effort is led by Lawrence, who you probably saw at the last webinar, to collect really good domain experts who are not directly maybe related to machine learning or optimization, but they have very deep expertise in their given fields of research. So for example, at the next webinar, we will have Emily, who works on business communication. And the hope is by bringing together different domain experts who are familiar with the idea of generative AI, but also have deep expertise in their own subjects of research, that in some sense we'll produce this body of knowledge that really says how is Gen AI, this one specific technology, going to impact different sectors of society. And to aid that process, there is this set of guidelines that we have developed at the Center of Intelligent Business, which you can access using the link that's been provided in the chat. So I'm hoping that beyond this seminar, that becomes a valuable resource to people in business, but also people trying to use Gen AI for their own personal gain, not in an organized activity. Okay, so I'll talk about generative AI. And to make sure that I'm not missing anything, let me quickly check if, yes, so good. So John has fantastically helped us in sending out the links for the guides to generative AI from the Center of Intelligent Business. Okay, so when I think about generative AI, I'll try to define what this term means. And then I'll give you a very quick one-page summary of how this piece of technology works before getting into how to use it, how this came about. So the most basic, and I think widespread, at least most widely acknowledged notion of generative AI is, for example, chatbots. So for example, ChatGPT is this famous piece of technology that I think has brought a lot of you to this webinar, which can produce novel pieces of text given some user prompt. And generative AI in general is this collection of technologies that's not restricted to producing just text alone. There are other examples. For example, there's Midjourney, which tries to produce images, very novel images, things that certainly do not exist on the internet, from text, text prompts. And there are also, for example, generative AI models that produce pieces of code, functional code that actually perform the task that you give them, in either through input-output examples or just describing what the program should do at a high level in terms of text. And each of these three modes of generative AI, they have seen some adoption. And although, for example, let me tell you about maybe two things. So there's GitHub Copilot. And what it does is that it offers a form of programming assistance to programmers so that they can write quickly large pieces of boilerplate code. Similarly, Midjourney has seen some adoption on the marketing side for people to produce logos, for example. But today what we'll do is we'll mostly talk about the first mode of generative AI, the setting in which we are trying to produce novel text from novel user prompts. And so, that's going to be our focus. These generative AI models are called language models. And I'll tell you very roughly in one slide from now how all of these language models function. Okay, and just to set the context, there has been great interest in generative AI, both from individual customers, individual consumers, and businesses. And not just that, from actually investors too. So I think one good figure to keep in mind is that Instagram needed about maybe 75 days to reach 1 million users. And for ChatGPT to reach 1 million users, it maybe took about 5 days. Fine, so it's one of these really viral pieces of technology in terms of how fast it got adopted. And similarly, if you look at the number of job listings in S&P 500 companies, The Economist reports, for example, that went up after ChatGPT was introduced by something like 5-fold. And this interest is not just limited to consumers and businesses. It's also the case that the investment in Gen AI has gone up at least maybe about 4 to 5-fold from 2020 to 2022. And it's not just true, again, that we just have interest from consumers, businesses, and investors, which I think about as the trifecta of technology adoption, there's also at least some concern from the regulation side. So again, it's this complete somehow storm of fast technology adoption. Okay, so and my promise was to talk more about language models, and maybe we'll broadly comment towards the very end on what the structure and the basic functionality of generative AI has to say in terms of its technology adoption. Okay, so here's what language models do. They implement a core and very basic piece of technology, a very basic sense of functionality. And that functionality is very simple. Given a set of words, actually a sequence of words, because the sequence matters in language, we want to predict the next word. And that's what a language model does. It's some sort of a neural net, and we'll see what neural nets are. That if you give it a few words, for example, Mary had a, then it produces not maybe just the next word, but it produces, in fact, a probability distribution over what it thinks the next word should be. Fine. So here, for example, it thinks that Mary had a red should occur with probability 0.2, given that Mary had a is a fixed piece of text that I cannot alter. For little to follow Mary had a, the probability would be something like 0.4, and something else like delicious would be maybe 0.2. And then what the language model does, given this very simple piece of functionality to predict, to create a probability distribution over the next word, given the past few tokens, is that it samples. Crucially, it randomly samples from this probability distribution. So here, for example, I might pick little. And then it can just repeat this process. So it says that little, although that it was not a word provided in the original prompt, I'll pretend that it's a word or token provided in the original prompt. And I'll run it through this neural network again to predict what the next word should be. So maybe the next time I'll predict something that makes sense. So Mary had a little mouse is a reasonable statement. Maybe that gets assigned a probability of 0.4. Mary had a little lamb, which is the poem itself. Maybe that gets assigned a probability of 0.3 and so on. And remember that every time I'm sampling from this probability distribution over the next word, which means that even if a mouse is maybe somehow more likely than lamb for the choice of the next word, it's still possible that I pick up lamb. Okay, and how are these probability distributions determined? It's determined based on training these language models on massive data sets. Fine, so this idea that you can take the past few words and try to predict the next word over and over again to create ever increasing and ever larger bodies of text, it's very useful. But it's predicated on this idea that you're able to create natural and well-defined distributions on what the next word should be. And this itself is learned from experience, from these huge collections of data set that have been crawled out of the internet. So in roughly this most famous, I guess, or at least GPT-3, which was a precursor to ChatGPT, was trained on something like 500 billion words. Tokens, I'm roughly translating it to words, although tokens are typically more numerous than words. Okay, and to give you a sense of how large this data set is, so I remember reading War and Peace, and yeah, it was a challenging experience because the book is fairly long. And all of the data that GPT-3 was trained on, again, a precursor to GPT, to ChatGPT, which has been trained on even more data, all of that data is about 1 million copies of War and Peace. Fine, so it's a fairly large data set. That's how language models are able to predict the next word in a reasonable fashion. Okay, so even from this very basic description of how a language model functions, we can draw some inferences. And these inferences already have some impact on how this technology gets adopted. Okay, so here are two very basic inferences that I can draw by looking at how a very basic language model functions. So the first observation that I have is that the completions for any initial piece of text, they are random, right? Every language model has a way of generating a probability distribution over the next word. And to generate a longer piece of text, we sample from this probability distribution. And what that means is that every time I run my language model, it's very possible, and in fact likely, that I'll get at least a slightly different output. Fine. And what this means is that language models have the ability to produce different novel completions for the same input. And not just that, this variety of outputs for the same input has advantages. That if you present these many different varied outputs to different users, if you can collect feedback to figure out which one of these outputs was better and use that to refine your language model. That's something that we're going to talk about at the very end. But it has some downsides too. So for example, if you sample from a fairly random distribution over the next word, then your language model might hallucinate. It might, or even produce sentences which are nonsensical. Fine. So just this idea of randomness, it's very useful. It's how we fine-tune language models. But it also creates some possibility of coming up with nonsensical outputs. The second bit that's really important to understand is, although intrinsically language models produce probability distributions over even larger and larger pieces of text, they never necessarily forget what the initial prompt was. In fact, the hallmark of good and modern and successful language models is that they're able to keep track of the initial piece of text that you put in, the initial piece of context that the user provided, even while writing like paragraphs and paragraphs of text. Fine. So the initial prompt matters a lot. And this has spawned a small cottage industry of people who try to sell ideas on how to create this initial prompt very nicely. For example, if you're trying to make the language model solve a logical task, people have gotten great mileage out of trying to put the initial prompt in a way that encourages chain of thought kind of thinking, right? So to think about the problem in a more causal way. Okay, so this is some observation about language models. So in general, what I'll try to do is I'll give you some description of how machine learning broadly works, and we'll draw similar inferences for what this technology enables and what maybe it does not enable very well, which is why further developments took place. Okay, so my basic method of organizing information in this talk is that I'll give you an introduction to machine learning itself, and I'll draw out what was lacking in these original machine learning models that led to Gen AI, and specifically to language models. Okay, so let's start with AI itself. So AI, I roughly think about as this academic discipline where people have the dream of building autonomous and intelligent agents. It had this history of having not very well-founded, or at least not very humble claims. So an early pioneer in AI, Frank Rosenblatt, for example, he claimed that, after inventing a very good and still used machine learning model, that they expect that the AI agent will be able to walk, talk, see, write, reproduce itself, and be conscious of its own existence. And certainly that hasn't happened yet. And this was in 1958. And so AI has this history of going through hype cycles and downturns and so on. But machine learning, I think, is a much more humble subfield of AI, although it's not humble in comparison to other academic fields, which has a much more modest aim. Forget intelligence. Let's just create algorithms that have the ability to improve from experience. This is certainly one path to AI, maybe not the only path. So a huge push towards AI that maybe even started at CMU with Herbert Simon and Alan Newell was to make an artificially intelligent agent by encoding pieces of logical knowledge, logical rules and basic pieces of knowledge. And instead, machine learning has this new idea that, maybe you should just try to make mistake and learn from your mistakes rather than having hard-coded rules. Okay, so that's the place of machine learning in artificial intelligence. It's a path to artificial intelligence, but certainly by no means the only path. And it's one of these fields that has seen very mature pieces of both sub-technologies and adoption. So I think when I think about machine learning, there's this one specific part of machine learning, which is called supervised learning, that I think is really a mature piece of technology, something that you can apply in practice and not worry about it failing on you. And very roughly, supervised learning, I think, can be described in just 2 words, that it creates prediction machines. It creates machines or algorithms that are very good at prediction. And this has been the success, the art in machine learning, that machine learning, it's much more humble than AI or even statistics. It doesn't care about something like p-values. It's not trying to uncover some hidden structure in the universe. It's just trying to make good predictions. And the art in machine learning has been to boil down non-obvious tasks that do not look like something that having to do something with prediction into prediction problems. And so one example of it is maybe that you have a data set, and this data set, well, you're trying to predict house prices from this data set. And what you're given is something like square footage of the house. So a very simple, humble machine learning algorithm is linear regression that tries to predict house prices from area given a collection of data, given a reasonably sized data set of past house prices and past house square footage, for example. Right? So this seems like a reasonable task. In this task, we are trying to predict a continuous quantity, what people would say is a regression problem. Fine. So this seems reasonable, but machine learning, the entire idea is that you take unreasonable problems and cast them as prediction problems. So let me give you an unreasonable idea. So an unreasonable idea is that you take an initial piece of text and try to predict an image whose caption is this initial piece of text. That's still, in machine learning verse, a prediction problem. But if you think about it, it's a very weird and artificial and somehow not even very well-defined prediction problem, right? So again, this entire art in machine learning is taking weird, somehow like conceptually extending this idea of prediction to go far beyond what I think people typically understand as prediction. And we'll see that. And in fact, that's how language models function. Okay, one of these assumptions in machine learning, and specifically in supervised learning, that language models do not adhere to, and they're really distinct in, is that the idea of supervised learning or building prediction machines, it focuses on very narrow tasks. But what do I mean by very narrow tasks? By something like predicting house prices, or if a given loan will default, given on certain lender or borrower characteristics. Okay, and why are these tasks narrow? Because there's an inherent assumption in most of supervised learning that the past data, the data that you've collected that you're using to pick what's the correct prediction machine, is representative of future data in a very specific way. So in very rough words, this representativeness has to take place in a very strict sense, which is that for any example, it should be equally likely for this data to be in the unseen or the seen bucket. And certainly, I don't think language models have this property. So language models are trained on data picked out randomly from the entirety of the internet. But that doesn't mean that businesses, when they're trying to apply language models or GenAI in general, they care about doing next word completion on a random sentence picked out of the internet. So we'll see what this weird phenomena that you're trying to somehow do tasks that look different from the data set that you have. What implication does that have for language models very soon? Okay, but this was machine learning. That in particular, the most, I think, well-formed, mature form of machine learning is supervised learning. And that really focuses on very narrow tasks, but it does them super, super well. And the game in machine learning is to boil down every single task that you can imagine into prediction. Okay, so there's this, and let me also add that in spite of all the hype about GenAI, I think it's still true that at least most people think, for example, Andrew Ng, who was an early pioneer in deep learning and machine learning, he thinks, for example, that most of the value that there is to be derived over the course of the next 3 years from machine learning still has to do with supervised learning, the most mature form of machine learning, rather than something like generative AI. And I think I'm in broad agreement with that statement. So, but there was this dirty trick about machine learning that its success was somehow limited to tabular data. So if your data initial data was something like an image or a piece of text or a piece of audio, then it didn't work very well. And it didn't work very well because machine learning algorithms, how well they did was limited by the way in which you represented your initial data. So there was this entire field of handcrafted, what people call representation learning. So there used to be like scores of PhD students in, for example, electrical engineering or computer vision, trying to design good initial representations of things like images or audio, so that you can then use standard normal machine learning to do, for example, speech recognition. Fine. So yeah, so this is, for example, an audiogram. You take a piece of audio and then try to somehow derive some sort of quantitative characteristics from this audio. And all of this was very handcrafted. It used to take like tons of PhD students for machine learning to work in every domain, because these PhD students would then figure out what's really important about the data. How do we represent it? How do we represent it in a meaningful fashion? Okay, so, and this was the place where breakthroughs started taking place during the last 10 years. So let me give you the first breakthrough that took place. And this took place around 2012 by Hinton, Sutskever, and Krzyzewski. And this idea was this field of machine learning that emerged called deep learning. Fine. And the idea in deep learning was very simple, that there are neural nets and they're a reasonable way of doing supervised learning. And maybe we should stack up these neural nets so that, you know, like each layer in a neural net, it processes information and it creates representations automatically. So the whole idea, the whole benefit of doing deep learning is that maybe it would work much better than normal classical machine learning algorithms, because it would refine the representation of the initial data incrementally and do automated representation learning. And in 2012, for the first time, I think there was this very nice point of time in history where people were able to pull together large enough data sets, enough compute, and enough tricks to make neural networks work in practice. And there was this very big breakthrough result that I think they were able to basically reduce the error on a natural image classification task, image recognition task, by something like 2x. Fine. And this happened in maybe 2012, but it didn't stop there. Every year, people would take larger and larger neural nets, and for the same task, they would reduce the error rate by more and more. So on the bottom, I have a graphic that says that, yeah, the initial maybe entry that reduced the error rate by half was 8 layers. And by stacking more and more layers of neural nets, by something like 150 layers, in 3 years from that point, the error reduced from something like 16 to 3. So a 4-fold reduction in error. Right? So there was this huge sort of gold rush where people would train larger and larger neural nets. They would create models that would do really well on natural tasks. Okay, so this was all fantastic, except that this is not the sole reason why deep learning was a very promising piece of technology. I think the more somehow consequential reason was that deep learning was not just true that it was very good at making predictions. It was, but it also had a side effect. When people really trained these neural networks, they would look at what each individual layer in the neural network did. And it looked like the following, that the initial input would just look like pixels for an image. The second layer of a neural net would still do something maybe that's not super related to what the task at hand is, but it would try to detect edges. The layer above would get slightly more inclined in the direction of the task that we're actually trying to conduct. So it would detect maybe contours or object paths. And here in a face recognition data set, the topmost layer would just have detectors that detect faces. So what deep learning did, and this was the long, sought promise of deep learning that was really realized after maybe 2012, is that they did, again, automated representation learning. And what that enabled was an entirely new paradigm of machine learning, where you take a huge data set and try to do some prediction task. Fine. And the idea, the guarantee that you have for doing this prediction task is not that you do this task well, but you also learn representations of the data that work well when you try to perform some other task. So again, this paradigm that really deep learning enabled was that you take a neural net, use it to do prediction on a very, very large data set, and then chop off the last neural net of this data set of the neural net, chop off the last layer of this neural network, and use this neural network as is to do some other classification task. And as long as you had maybe, instead of millions of examples, like even tens of thousands of examples, then you could do the second task reasonably well, because you have already done the hard part. You have already learned how to represent natural images. So this was the idea behind transfer learning, or in this talk, we'll call it fine-tuning. Fine, and all of this was great. This worked very well for vision. It, I think, revolutionized computer vision to at least not high-resolution computer vision. Okay, and what I'll do next is I'll tell you how do language models come into this picture? Why weren't we just satisfied with something like deep learning? And that has to do with the second dark truth about deep learning, that deep learning, it required tons of labeled data. So although we would build this very fancy, very nice deep learning models, the first deep learning model that you would build that you would later use for different classification tasks would still need millions of examples. And these millions of examples were labeled, which meant that there was one person or a team trying to label each of these millions of examples and say, well, there's a face here, there's no face here, or there's a giraffe here, there's a monkey there, and so on. Fine, and that was an arduous task. So although we were automating learning, the initial data that was used to train these machine learning algorithms still had to be labeled by humans. And the basic prompt that led to machine language models was, why not somehow automate the creation of labeled training data itself? So let me give you a very concrete example, and this is how it took place in language models, or at least in the context of language. So in language, people have there's a very nice and intuitive idea that a word is known by the company it keeps, very roughly. So it's called the distributional hypothesis. And what it basically says is that semantically similar words that mean the same thing, well, they occur in similar contexts, right? So if I say this is a red bottle and this is a blue bottle, these statements seem equally likely. So it must mean that red and blue, well, they're not maybe synonyms, but at least they refer to the same attribute of a bottle. Fine, and what people did this was a paper by Mikolov et al. At Google, I think it may be 2014 or 15. And here's what they did. They took a large corpora, large pieces of text. And what they did was they would say that, let's try to pretend that we forgot some random pieces, some random words in this big document. And then they would use the surrounding words to train a neural network to predict these randomly removed pieces of text, randomly removed pieces of words from this huge corpora. So by doing this, this is a meaningless prediction task in some sense, because we know what the original corpora was. But the representations that we built based on this artificially created prediction task were super useful. For example, this is a two-dimensional slice of the representation we got for individual words, and you can use it to answer analogy questions. For example, you can take the vector representation of a neural net for the word king. You can subtract from it man and add woman and say, what's the closest word to king minus man plus woman? And you would automatically get queen. Fine. So there was this degree that these representations, they were semantically meaningful, that you could just subtract out certain words to produce what should be semantically correct result of this addition and subtraction. Okay, so this was absolutely, it was not maybe super immediately useful, but people were really taken by this in the sense of they saw the promise of this piece of technology. This general idea that you should create fake prediction tasks from unlabeled data, and that the fact that you can do it for free without involving humans in the loop is called contrastive learning, and it has found its uses elsewhere, even in vision. So for example, you can think of, if I take random crops in the same image, they should be similar rather than random crops from different images. So it also applies to other domains. Okay, so again, these by themselves are not language models. They're a good representation of initial pieces of text. To create a language model, you needed a notion of memory, because you have a bunch of text and you're trying to keep track of some semantic notion of what's happening in the story so far. Right? So for example, in a good Chekhov story, for example, Chekhov's gun, if a certain entity gets introduced at the very start, it matters at maybe the 75th percentile mark. Okay, so this idea that you should have a notion of memory in a neural net, that's old. There was a realization of this idea using neural nets, which were called recurrent neural nets, which were notoriously difficult to optimize. So you would throw like huge computing powers at these tasks, but they would never give good results. And yeah, like I and others, I think a lot of people had these very small toy models where you could definitely say that recurrent models that process words one at a time, they are somehow, much more difficult to optimize than models that take all tokens at a time and then try to produce an output. Okay, and in something in 2017, there was this alternative idea of how do you produce models that have a notion of memory, yet do prediction very well, which was introduced by, again, researchers at Google Brain by Basmani et al., which was this idea that maybe I should not train a recurrent neural net and instead train what people call a transformer. So very roughly speaking, the idea in transformer is that it's not unlike recurrent neural net where you start at the first word, read the entire book at the very end, and then try to answer a question. It says that maybe you should start highlighting different pieces of text that you think are important. And maybe you should make 3 passes, parallel passes over the entire book while highlighting separate pieces of text. This act of highlighting, it's called an attention mechanism. It tries to judge how much a certain word matters for the query that you're being asked. It's a very non-sequential model of information processing. And it's one that makes optimization super nice. So that's what people figured out. And it led to a huge arms race in the space of language models. So these were the first language models, where what people did is that they scaled the amount of data that these models were taking. So something like GPT-2, which was an earlier precursor to GPT-3 or ChatGPT, was trained, had something like 1.5 billion parameters. And within a year, GPT-3 was released, which had something like 175 billion parameters. So maybe 100x more. And that's not even, until late 2022, it was not even the largest language model. There was something from, I think, Microsoft, which was called Megatron, which was even larger, right? So this idea that you should maybe just train larger and larger neural nets to get better and better representations of text, that came into practice. Okay, and these language models, they were very nice. You could take these representations and try to solve a different supervised learning text from that point on by having a few more examples. That was always possible. You could do supervised fine-tuning, this idea that we looked at, chop off the last layer of the neural net and train a separate neural net for every single task that you actually care about, not just predicting the next word. But more crucially, they enabled a new mode of transfer learning, of doing well on subsequent pieces of tasks, subsequent tasks. And this new mode. It's called in-context learning. And one major contribution of language models is that this in-context learning, it's very easy to do. It does not require any coding. And nevertheless, it performs almost as well as this procedure of chopping off the last layer of neural network and so on. So large language models really lower the gap between fine-tuning and in-context learning. And this has implications for how people use these models for democratization, and we'll get to that very soon. Okay, so again, roughly when I think about in-context learning, you still have a data set, maybe just tens of examples or 20 examples. And instead of using them to tune the weights of a neural net, to chop off the last layer and so on, I'll just take this entire data set and pass it as a textual input, as prompt to my language model. Fine, so all of the learning, it's happening in, just providing the initial context window, the initial piece of text that this language model would take. So for example, here is an example where I'm trying to do something like sentiment classification. I just copy and paste some examples of good sentiment classification in my text box. And I then say, if the next review is good meal, what's the sentiment? Again, a very simplified example, but I hope you get the idea. Okay, and it turns out, yeah, so this was already very useful in the sense that language models still really lowered the gap for how much technology would it take for these pieces of, interesting bits of machine learning models to be adopted. And the final bit I should tell you is that, yeah, like it turns out these models, they're just trying to predict the next word. So they're not necessarily very good at keeping up conversations. So there is this other set of ideas. So if you asked for to a normal language model, for example, what should I say after saying that explain moon landing to a 6-year-old in a few sentences, it would say explain the theory of gravity to a 6-year-old, explain the theory of relativity to a 6-year-old, and so on. Because these are natural questions that follow the initial question, which is explain moon landing to a 6-year-old. Right? So they're not very good at following instructions, keeping up conversations. So these next set of the ideas that came into this large language model space were by OpenAI, who looked at how do you this problem of how do you align these language models to keep up conversations, to follow user instructions. And they did so by going back to this idea that maybe if I take a few examples of what good responses are to good questions, then I can get my large language model to follow that example. And again, by this idea of using supervised fine-tuning, and is this response good or not, based on every random generation, they were able to use these very well to follow instructions and keep up conversations. And that's what ChatGPT is on top of a very large language model. Okay, so let me post the last slide before we get into questions, because I think I'm running out of time. So there's this hope. So there's this mismatch, let me start, on the industry side where, well, language models, they're great. In general, generative AI is great, but for specific modalities, for something like texts or images. And if you look at how people chat or talk about generative AI in newspaper columns and technical reports, they talk about them as general decision-making agents. And I think, like people are trying to, for example, revolutionize supply chain using generative AI. How does that happen? So I don't think we have the tools for that yet, but there's hope. And the hope is this term called foundation models. And what foundation models aspirationally try to do is they try to recreate the magic that large language models had in other domains. For example, can I create a generalist robot by taking a lot of data about how robots operate and try to make a robot that does a specific task super well? Can I try to learn across supply chains, across multiple industries, to do well for my own supply chain task after I've seen all of this data? So yeah, there's hope, but there's no concrete flavor of what, that we have a result that does this very well yet. So I'll end there. I'll talk about uses, pitfalls, and possibilities very soon. and mostly through the question answer format. And I'm hoping I'll get to reuse a few of my slides, but let's move on to questions. Okay, so again, thank you all for your attention. Next, what I'll do is I'll address questions from the chat, and I'll also try to address a few questions that John forwarded to me before the talk, based on the questions that you filled on the alumni, on the talk registration form. Okay, so again, thank you, everyone. Okay. So great. So we have plenty of questions, and what I'll try to do is to address as many of those as possible before the session ends. So and again, so I think the message that I have from John is that I shouldn't read out the people, at least the names of the people asking these questions, because we might not have the correct consent procedures in place. So what I'll do is I'll anonymously read these questions. Okay, great. So here is the first question. So, well, Steelers Fan 1 asks if there are any blogs or books to understand more about, well, predictive supervised learning and large language models, and a bit more on the tech and algorithm side. Okay, so the interesting bit about, I think, generative AI is that it's still a very new piece of text. I think most of the outsider to machine learning interest in generative AI has been post the release of ChatGPT. So unfortunately, I do not know of very, very good resources that I could recommend to you and not take a second look. But there are these very nice set of videos by Andrew Ng. He was one of, he was a pioneer in deep learning, and he made a lot of these vision-based deep learning models work. So if you, I think, go to deeplearning.ai, that offers, I think, free courses on how to use, generative AI for technology adoption. Okay, so let me maybe try to attempt the second question. So Steelers Fan 2 asks if, what are ghosts in the machine? How do you prevent them? And what are 3 most profitable use cases for the future? Great. So I think by ghost, what typically I think people mean is this problem that, well, that you take a very good language model and you ask it reasonable questions, but it might not give you reasonable answers. Sometimes if you ask it factual questions, it does not even necessarily tell you, the responses might not be factual. It's not just that. Microsoft at some point released this Twitter bot based on a language model that people could converse with. And as you would imagine, after a few days, the experiment went haywire. It was insulting people left and right continuously. So I think what happens is that these language models, I think there are 3 or at least 2 different issues that I can try to quickly address. The first issue is that these language models, they have a tendency to not output what is factually true, because that's not how they were trained. They were trained to predict what looks likely as the next word, right? So it's not true that they're going back into a database and looking up some original answer. What people have found very useful to mitigate that tendency of the language model is, well, so there are specific kinds of language models that give you a proof of attribution. So if you ask them for a fact, they'll say, in your context prompt, where you supplied maybe the employee handbook, there is this small piece of text that I'm referring to when I'm giving you this answer. So that's one. They've also found that this idea of supervised fine-tuning and learning from human feedback, if you do it enough number of times on a vanilla language model, that reduces hallucinations by quite a bit. And in terms of just not having a toxic model, this third, I think, doomsday scenario, I think, again, if you curate what the language learns from very nicely, this does not happen. So I think the problem with Microsoft's Taya model, this Twitter bot that went completely berserk, was that it was learning from Twitter users. And that might not have been a very good source to begin with. So again, and maybe I should mention, there's a very intuitive and nice way in which, for example, a local Pittsburgh company, Duolingo, tries to monitor how people chat with generative AI. So I think they put some version of GPT-4 in basically in conversational situations with people so that they can learn language better. Duolingo is a company that helps you really enables you to learn any language, again, using just a mobile phone app. And what they do is that they place a second normal supervised machine learning model, and it tries to make sure that the answers that this generative model is giving out have the correct tone and intonation and so on. So you can certainly create other safeguards against a language model going haywire. It doesn't completely stop it, but at least it provides some level of mitigation. Okay, so to quickly maybe address some other questions. So does LLM only apply to text and language? How would AI work for things related to video, such as identifying a proper golf swing, suspicious activity, and so on? So, okay, so I think two responses. So one is that even ChatGPT, it's now a multimodal, generative AI model. It can accept if you want something like an image. Videos have always been a bit challenging for just deep learning in general, and hence for generative AI models too. And I think there's some hope that this foundation models kind of idea, maybe you can create a very large generative AI model that can ingest any kind of input and produce any kind of output that you want. But for videos, I don't think that it's there yet. So generative AI for videos, it's typically what it will do is that it will try to, if you give it 2 frames, it will try to interpolate in between. Or maybe you can say something like, remove this plant that's obstructing the view on the top right corner. And maybe it will be able to do it. But to produce truly novel pieces of content, I think for videos, we are not there yet, because deep learning for videos is, videos are many frames stacked together. So it's a much more high dimensional space. And I don't think that's very easy to do. Okay, so just to ask the final few questions before maybe we run out of time. So do you see that we are at the pivoting point of LLM and ML in terms of technology itself? If not, do you see applications based on these technologies to become outdated soon? So I think it's here to stay, basically. That I think it's the case. So I think, again, so just very broadly, the original idea of machine learning, like the thing that people did in between 2000 and 2010s, or even before, or even a bit after, was that for each narrow task, you should have a large data set that's just there for that narrow task. And then if the number of examples that you have is large enough, then you do well on that specific task. And this idea that I have many related tasks that my machine learning model is trying to perform, and I can borrow some piece of information from one task and use it in the next task because these 2 tasks are similar, is what transfer learning or even generative AI / language models enables. So I think that's here to stay. This idea of amortizing both data and compute across tasks, it's a very natural one. And I would be at least surprised if that goes away. If anything, I think the problem with deep learning is that by default, if you try to use it in the conventional mode, where you're trying to use it to solve narrow tasks, it requires a lot of data. And this provides a way to mitigate that. Sorry, I think that time might be up, but I'm happy to take more questions offline. In the sense, yeah, so I think John shared my contacts on the CMB webpage, and I would be happy to engage offline too if you send me emails, for example.
Well, thank you very much, Karan, Professor Singh. We really appreciate your presentation today. I think for a lot of us who don't have deep technical understanding in this, you explained it very well and gave us a good perspective on it. So I would encourage our alumni, if you've got specific questions, to reach out to Professor Singh here at the school, or you could come if you were a student here, an undergrad, you'd be taking his course. If you were part of our Masters of Business Analytics, our new one-year master's program, you'd also get a chance to have him teach in the classroom. But thank you for joining us on our virtual classroom today. We know there's always more questions, but we hope we'll see you next month on our next generative AI webinar. And please send us your questions and stay active with us. Remember, you're students for a few years here, but you're alumni for a lifetime. Thank you.